The numerical question is, a Butterworth low-pass filter has to meet the following specification. Passband gain Kp is equal to -1 dB at omega p is equal to 4 radian per second. Stop band attenuation is greater than 20 dB when omega s is 8 radian per second. Determine the transfer function HA of S of lowest order. To determine the transfer function of this filter, we have to know the order of this filter, that is n. We know the formula n is equal to log of 10 raised to minus kp by 10 minus 1 divided by 10 raised to minus ks by 10 minus 1 whole divided by 2 log omega p by omega s. Substituting the values of kp, ks, omega p and omega s, we got n is equal to 4.2897. Even after the decimal it is 0.1 or 0.2, we have to take the next integer, hence n is equal to 5. This filter is of fifth order. These are the Butterworth polynomial for different n values. In this question, our n value we obtained is n is equal to 5. Therefore, the Butterworth polynomial is s plus 1 into s square plus 0.6180s plus 1 into s square plus 1.6180s plus 1. After obtaining the value of n, transfer function is equal to 1 divided by Butterworth polynomial. This is the Butterworth polynomial. After doing the polynomial multiplication, we obtain the transfer function h5 of s is equal to 1 divided by s raised to 5 plus 3.236 s raised to 4 plus 5.236 s cube plus 5.236 s square plus 3.236 s plus 1. It is very helpful if we remember this transfer function before opening the bracket and after opening the bracket. After obtaining the transfer function, we have to calculate omega c, that is cutoff frequency. We know the formula omega c is equal to omega p is divided by 10 raised to minus kp by 10 minus 1 raised to 1 by 2n. Substituting the values of omega p as 4, kp as -1 and n as 5, we obtain omega c is equal to 4.5787 radian per second. After calculating the cutoff frequency, we are asked to design a low-pass filter. Hence, we have to apply the transformation low-pass to low-pass transformation. To apply low-pass to low-pass transformation, we have to substitute s divided by omega c in place of s. We have obtained omega c is equal to 4.5787 radian per second. This is the transfer function we have already obtained. Substituting s by omega c in place of s, we can obtain the updated transfer function. In every place of s, we have substituted s divided by 4.5787. After calculating this, taking the LCM as 4.5787 whole power 5 and keeping the numerator and denominator appropriately, we get transfer function h5 of s is equal to 2012.3963 divided by s raised to 5 plus 14.817 s raised to 4 plus 109.675 s cube plus 502.4953 s square plus 1422.26 s plus 2012.3963. Evaluating this transfer function at omega p is equal to 4 radian per second, we have to evaluate this at omega p is equal to 4 radian per second. We know that s is equal to j omega, where omega is 4 radian per second. Substitute 4j in place of s. 4j raised to 5 plus 14.817 4j raised to 4, and similarly wherever s is there, substitute 4j. When we substitute 4j, this becomes 4 power 5 and j power 5. 4 power 5 into j power 5. J power 5 can be written as j square into j square into j. J square is -1 into -1 and this j remains as it is. Minus into minus plus, therefore this becomes 4 power 5 into j. Similarly, for 4 power 4 into j power 4, j power 4 can be written as j square into j square, that is minus 1 into minus 1 becomes 1. For j cube, j square into j, where j square is minus 1 and j remains as it is. After solving this, we get two terms, that is one constant term and one imaginary term. We have to find the magnitude 20 log h of j omega. This is a real term, whereas the denominator is imaginary term, real plus imaginary. For this we have to find the magnitude. We know that magnitude of a plus jb is equal to under root a square plus b square, where this is a and this is b. 20 log h of j omega is equal to 20 log of numerator as it is, apply a square under root a square plus b square for denominator. After solving this, we get 0.892256. 20 log 0.892256 is minus 0.99 dB.